In this section, we're going to look at the motion of charged particles in an electric field. So previously we talked about the actual electric fields themselves and how charges stack up around certain shaped objects, and we talked about that corona discharge effect of particles concentrating around sharp points. Now we're going to look more into how does an object actually move in a field. So the first thing is, what are we going to cover today? This is our learning outcomes. So we're going to talk about that electric fields store potential energy. We're going to talk about the motion of charged particles and its potential, the work done, the electron volt, and the fact that we use the equation that work is Q delta V, which we'll explain. You'll also need to know how to convert from joules to electron volts, and in the opposite, electron volts back to joules. Firstly, let's consider the gravitational potential field again, going back to just plain old Earth. We know that if we have an object and we drop it, it falls, it accelerates, and it's being pulled by that gravitational field. So it's free to move. Therefore, it's going to gain kinetic energy when we drop it. That kinetic energy had to have come from somewhere, and we know from conservation and from previous physics that it came from the potential that was given to it by that field or by the person that lifted it in the first place. So we've called this gravitational potential energy so far. That's not any different to if we consider an electric field. Let's say we take a charged particle B, and remember this is a positive charge, and it's in a plus Q field. So particle B has its charge, it's repelled by Q because they're the same. So it's going to be forced along the direction of the electric field lines, and it's going to move towards A. Therefore, if it's thrown outwards towards A, it's gaining kinetic energy, just like the falling object in the last example. So where did its kinetic energy come from? It must have had potential, and in this case, we just call it electric potential energy, just like gravitational, but it's done by the electric field, so it's electric potential. Here we've got an example of two different types of charged plates, or field lines. In the top example, we've got a negatively charged plate, and the field lines are moving towards it. So if I had a positive and a negative charge, I can see what's going to happen to them if they're placed within that field. The positive charge is attracted to the negative plate, so it's going to speed up, it'll accelerate towards it, therefore it's going to gain its kinetic energy and it's going to lose whatever potential it had. On the flip side, if I take the negative charge, it's repelled, so if I force it to get closer to the negative plate, it's going to gain potential because it wants to launch back in the other direction. So have a think about what would it be for the bottom case. If I flip this, and I now have my positive plate with the positive and the negative charges, what one is going to gain potential and lose kinetic, and vice versa. When we've talked about potential previously in terms of gravitational potential, we've said that, and we know that lifting a mass requires work to be done on the mass or against the gravitational field. So in order for you to lift a ball up and give it potential energy, you've done work on the ball or you've done work against the gravitational field. If it's falling, once you've let go of it, the gravitational field is then doing the work on the object, and that's why it gains kinetic energy. So this gain of potential and kinetic is by the work being done on the object or by the object, or on the system and by the system. So we've talked about work previously in stage 1, and hopefully you remember that it's the force times the distance. Work is equal to Fs. But in terms of gravitational potential, it's also the mass times the gravity times the height, where the h is just the height through which the mass is raised in the field. In the same way as this, when a charged object is moved through an electric field, its potential and its kinetic energy changes, so the work done on it or by the field acts in exactly the same way. So we can see this in this example here. When we talk about electric potential difference, so this term you should have seen previously, and certainly the term potential difference is pretty well known, and we often call it just the volt, but it's actually the potential difference between 2 points in an electric field is the work done per unit of charge, and it's done in moving a positive test charge between 2 points. So just like lifting that ball through a gravitational field, if we move a positive test charge from point A to point B, we had to have done work on it. And doing that is the electric potential difference. So we call this the volt. It's equivalent to 1 joule per coulomb. So a joule of energy done to move it against or move a charge of a coulomb. The potential difference is work per unit charge. So we can just write that as the work done divided by the charge. And we can rearrange this in terms of, if we start with delta V, which is potential difference, the change in potential, change in voltage, it's the work done divided by Q. Then what I can actually do is I can rearrange that and I can get an expression for the work done. If the potential is the work divided by the charge, then the work is just the charge times the potential. So this tells me that if a charge is moved in the direction opposite to the force exerted on it, then work is done on the charge. So the concept of work being done on an object or by a field is really important here. So in this case, you can think of it as a bit like paddling downstream or upstream. If you are moving against the stream is trying to push you downriver and you're fighting against it, then you are doing work against the stream. So you're doing work on the object, the canoe, whatever it is, to oppose its motion. And the field is the thing, in this case, the electric field, it is the thing that's actually storing that potential. The object itself can't necessarily store potential, so we would say that the field is storing it. On the flip side, if we take a charge and it's free to move in an electric field under the action of that force, so you're on that river and you just stop doing anything and then you're pushed downstream, for example, then we would say that the electric field is doing work on the test charge, just as the river would be doing work on you to push you down the stream. So you're gaining kinetic energy that is being done by the work on the stream, just as the charge is gaining kinetic energy, which is done by the work that the electric field is doing on the charge. So if the work done is equal to the change in kinetic energy, we can say that the kinetic energy change is Q delta V, which is the work, and that's equal to half mv squared, which is just the kinetic energy formula. So now we've got an expression in terms of work in kinetic energy and also work in terms of a charge and a potential. So these two formulas are very important for solving problems. Now have a go at it. So in these questions here, you use this concept of work being Q delta V and work being the kinetic energy formula. So pause the video now, I'll give you a minute or so, and then I'll show you the answers and we'll go through it. Okay, so in this case, the work done on the charge, we know the charge and we know the potential difference. So this is just a Q delta V situation. So I plug it in, I've got the charge that I was given. Remember that they gave you the unit, so it's a milli. The prefix is millicoulomb, so it's 10 to the minus 3. I times that by the potential difference and I get 8 joules of energy. That's the work done. Now I want the kinetic energy that's gained. So I'm going to use a different formula. But in this case, you would look at it and you're like, well, I don't know the mass of the charge. I don't even know the velocity of the charge. But what is the kinetic energy gained? Kinetic energy gained is the work done. They're equal to each other by the conservation. That's where it came from. So anytime that you know the work done and you want to know the kinetic energy, they're just equal to each other. Now if I want the speed, I need the kinetic energy formula. And in this case, they give you the mass of the object. So everything that I know except the velocity, and velocity is what I want to find. So I plug in my values. I've got the work is Q delta V, which is half mv squared. Rearrange for velocity and I get 1.1 times 10 to the 8 meters per second. All right, so now we're going to talk about the electron volt. The electron volt is used a lot in electric fields and electric circuits because it's a more appropriate unit. Just like in astronomy, we use the AU or the light year because it's a more appropriate unit than writing thousands, millions, etc. of kilometers or meters. The electron volt is a more applicable unit for electric fields because in this kind of case with a subatomic particle, a joule is a huge amount of energy. Subatomic particles are like 10 to the minus 19. We don't want to write that all the time, so we need another unit that we can use that's a bit more convenient. The electron volt is this unit. It's defined as the work done when an electron moves through a potential difference of 1 volt. So you take an electron, you move it through a delta V of 1 volt, then the work done in order to do that is 1 electron volt. That's its definition. So when we looked at those previous formulas, we said the work is Q delta V. The electron volt is the work done on an electron. So the Q of that, the charge of the electron, is the 1.6 times 10 to the minus 19. And we just multiply it by our delta V, and we get that the electron volt is 1.6 times 10 to the minus 19 joules. So if you ever forget this number, it's on your formula sheet. It's also the charge of the electron. You notice that because it's just times by 1 volt, it's equivalent to the charge of the electron. So to go from an electron volt to a joule, we times by 1.6 to the times 10 to the minus 19. And just as if we were rearranging maths, if I wanted 1 joule, I would divide by the 1.6 times 10 to the minus 19. So here's a couple of example questions to use that. Firstly, you're given the delta V of the electric field. Sorry, no, you're told that the particle has 2.5 electron volts of kinetic energy. They just want you to convert it to joules. So a conversion. Then if it gains 7.2 times 10 to the minus 16 joules of energy, convert this to electron volts. Then you're told to calculate the kinetic energy gained as it accelerates through the potential using joules and electron volts. And then the last case is just talking about calculating the charge or the change in potential of these objects. So pause it now, have a go at these questions, and then I'll show you the answers. All right, so in the first one, we were told that it's 2.5 electron volts. I just multiply by that charge of an electron because it's what is the delta V times the charge of the electron. I get my joules. So 4 times 10 to the minus 19 joules. In the next case, I was given joules and I wanted electron volts, so I divide by the 1.6, and this is my answer in this case. So 1 you multiply, and in this case you divide. In the last case, I use my Q delta V. I've used the charge of the electron, 1.6 times 10 to the minus 19. It was in a delta V of 6 times 10 to the 3. So again, I just plug in my delta V, I get my number, and Q delta V is always in joules. So my 9.6 times 10 to the minus 16 is in joules. It should be a giveaway because the number is very small. If you have a tiny number like 10 to the minus 16, that should be a giveaway that it's joules because it's not a great unit. Then when I convert to electron volts, I get something much more reasonable, 10 to the 3. So if you're not sure which unit you've resulted in, think about its size. For a lot of this case, a tiny number is going to be joules, and a more respectable number is going to be electron volts. Now if I look at this, I've got a charge of 1e, so an electron. So the charge is 1e, it moves through a delta V of 300 volts. Its potential is just 300 electron volts because it's the electron times the voltage. Now if I've got a positive charge, so a proton, and it's moved through a difference of 2500 volts, what is the work done on it? Well, remember the charge of a proton is just the opposite of the electron. So it's the same number, but in a positive direction. And I don't care about the direction, so the work done is just exactly the same. It's 2500 electron volts. If I took an alpha particle, which has a plus 2e charge, and it's moved through a potential difference of 400 volts, the change in potential is going to be the charge times the delta V. So it's going to be a plus 2 charge times 400 volts. I get an 800 electron volt potential. Last case, exactly the same. I've got a negative 3, a nitrogen ion, so it's a negative 3e charge times by 50. My final charge is 150 electron volts. So these are the workbook questions for this module. Page 152, question 1 and 2 is just energy and work problems, similar to the examples that we've been through in this lesson. And question 3 is on the synchrotron. So we haven't talked about what that is yet. We'll talk about that in a couple of lessons' time, but you should still be able to have a go at that question based on what we've covered today.